Welcome! In this session, we'll tackle problem number 416, partition equals subset sum. This problem challenges us to determine whether a given array can be partitioned into two subsets with equal sums. We'll explore different approaches, break down the solution, and provide insights into its complexity. Let's dive in. In this problem, you are given an array of integers, nums, and your task is to determine whether it is possible to partition the array into two subsets such that the sum of the elements in both subsets is equal. Essentially, we want to split the array in a way that both parts have the same total sum. The input will be an array nums of length n, and the output is a Boolean value, true if this partition is possible, and false otherwise. For example, if the input array is 1, 5, 11, 5, the answer is true because it can be partitioned into two subsets with equal sums. To explain the first example, the array 1, 5, 11, 5 can be split into two subsets, 1, 5, 5, and 11. Both of these subsets have a sum of 11, which meets the condition for a valid partition. On the other hand, for the input 1, 2, 3, 5, the output is false. This is because the total sum of the array is 11, which is an odd number. Since an odd total cannot be divided into two equal parts, it is impossible to partition this array into two subsets with equal sums. In another example, the input array 2, 2, 3, 5 has an output of true. Here, the array can be partitioned into 2, 3, and 2, 5, where both subsets have a sum of 5. Moving on to the constraints, the array length, n, is between 1 and 200, and each element in the array is between 1 and 100. A key observation is that this problem can be reduced to a subset sum problem. Can we find a subset of numbers in nums that sums to half of the total sum? If the total sum is odd, the answer is immediately false. To solve this efficiently, we can use a dynamic programming approach, either with a 2D DP table or a space-optimized 1D DP array, to track which subset sums are achievable. To solve the partition equals subset sum problem, we need to determine if the array can be split into two subsets with equal sums. This challenge is a well-known dynamic programming problem, but let's start by considering the brute force approach. The idea here is simple: generate all possible subsets of the array and check if any subset has a sum equal to half of the total sum of the array. If such a subset exists, the array can be partitioned. However, there are some key observations to make. First, the total sum of the array must be even. If it's odd, it's impossible to split the array into two equal parts. Second, the process of generating all subsets is highly inefficient because it involves recursion or bit manipulation, which leads to exponential time complexity, specifically O(2 to the power of n, where n is the size of the array. Additionally, this approach requires O(n) space for the recursion stack. Clearly, while this method works for small inputs, it's impractical for larger arrays, which is why we need to explore more efficient strategies. Now, let's move to the dynamic programming approach, which reframes the problem as a subset sum problem. The goal here is to determine if we can find a subset of the array whose sum equals half of the total sum. To solve this, we use a DP table, where dp I, j, indicates whether it's possible to achieve the sum j using the first I elements of the array. The transition logic is straightforward. For each element, we decide whether to include it in the subset, which means checking dp I1, j nums, I, or exclude it, which means relying on dp I1, j. The base case is that a sum of 0 is always achievable with an empty subset, so dp 0, 0 is true. To optimize space, we can use a 1D array instead of a 2D table since each state depends only on the previous row. This optimization reduces the space complexity to O, target, where target equals half of the total sum. The time complexity remains O, and asterisk target, which is significantly better than brute force. It's also worth noting that greedy methods, such as sorting the array and partitioning subsets heuristically, fail to guarantee correctness and are therefore unsuitable for this problem. With these considerations in mind, the optimized dynamic programming approach with 1D space is the most effective strategy. It balances efficiency with correctness, avoiding the prohibitively slow nature of brute force while maintaining accuracy. By reducing the memory usage compared to a 2D DP table, it's also practical for handling larger arrays. When comparing trade-offs, the brute force method is simple but far too slow for larger inputs. The traditional 2D DP approach is correct and faster than brute force but still requires an asterisk target space. The 1D optimized DP approach, on the other hand, achieves correctness and speed while using linear space relative to the target sum, making it the optimal choice. Finally, while greedy methods are fast, they fail to guarantee correct solutions and are unsuitable here. Overall, the 1D DP optimization provides the best balance, offering a polynomial time solution with minimal space usage. To solve the partition equals subset sum problem, we need to determine if we can split the array into two subsets with equal sums. The first step in our algorithm involves analyzing the problem. A key observation is that if the total sum of the array is odd, the partition is impossible since you can't divide an odd number into two equal integers. For example, if the array is 1, 2, 3, the total sum is 6, which is even, so a partition might be possible. However, if the total sum were 7, no valid partition could exist. With this in mind, our goal becomes finding a subset of the array whose sum equals half of the total sum, which we call the target. This transforms the problem into a classic subset sum problem. We need to decide if there exists any subset in the array that adds up to this target value. To solve this, we use a dynamic programming approach, where we define a DP table DP I, j, to represent whether it's possible to form a subset with some j using the first I elements of the array. If DP I, j is true, then such a subset can be formed, otherwise, it cannot. Next, we define the base cases for our DP table. First, DP 0, 0 is true because we can always form a sum of 0 using an empty subset. For all other sums j greater than 0, DP 0, j is false because it's impossible to form a positive sum with 0 elements. Moving on to the transition relation, for each element in the array, we have two choices, exclude it or include it. If we exclude the current element, then the value of DP I, j remains the same as DP I1, j. If we include the current element, we first check if the current sum j is at least as large as the element's value. If so, we check whether the remaining sum, j nums I1, could be formed using the previous elements. Combining these two cases, the transition rule becomes dp I, j equals dp I1, j, or dp I1, j nums I1. After populating the dp table, the final step is to check the value of dp n target, where n is the length of the input array. If dp n target is true, it means we can form a subset with the required sum, and therefore, a valid partition exists. Now let's highlight some key insights behind the algorithm. First, the problem is effectively reduced to a subset sum problem, which simplifies our approach significantly. Another important detail is to exit early if the total sum of the array is odd, as this guarantees that no valid partition exists. Additionally, we can optimize the space complexity of the solution. Instead of using a 2D DP table, we notice that each state in the table only depends on the previous row, which allows us to use a 1D array to save memory. This reduces the space complexity from n asterisk target to target, where n is the number of elements in the array. We also need to account for edge cases, such as an empty array, which should return false, or a single element, which can only return true if the element equals the target. Finally, the algorithm must handle large numbers efficiently, ensuring it works within the problem's constraints. With these optimizations, the time complexity of the solution remains n asterisk target, while the space complexity is minimized to target. Here's the pseudocode for the algorithm. First, calculate the total sum of the array. If it's odd, return false immediately. Next, determine the target sum by dividing the total by 2. Initialize a 1D DP array of size target plus 1 with all values set to false, except DP 0, which is true since a sum of 0 can always be formed. For each number in the input array, iterate over the DP array backward from target down to the value of the current number. Update each DP j by checking if it's already true or if the remainder j number was achievable in the previous state. After processing all numbers, the result is stored in DP target. If DP target is true, it means we can partition the array into two subsets with equal sums, otherwise, we cannot. This Python implementation solves LeetCode problem number 416, partition equals subset sum, using a dynamic programming approach. The goal is to determine if the input list nums can be partitioned into two subsets with equal sums. Step-by-step explanation. Step 1 calculates the total sum of all elements in nums. If the total sum is odd, it is impossible to divide the array into two subsets with equal sums, so the function directly returns false. This is because a subset sum of total_sum/2 would not be an integer. Step 2 calculates the target sum for one subset, which is total_sum/2. This represents the value we aim to achieve using a subset of numbers from nums. Step 3 initializes a Boolean dynamic programming array dp of size target plus 1, where dp, I, represents whether a subset sum of I is achievable. The base case is dp, 0, equals true, as a sum of 0 can always be achieved with the empty subset. Step 4 iterates through each number in nums. For each number, it updates the dp array in reverse order, from target down to number. The reverse iteration ensures that each number is only used once in the subset sum calculation. For each possible sum t, it updates dp, t, to true if dp, t number, is true, indicating that t can be achieved by adding number to a previously achievable sum. Step 5 checks if dp, target, is true. If so, it means the target subset sum is achievable, and the array can be partitioned into two subsets with equal sums. Otherwise, it returns false. This implementation is efficient, with a time complexity of O, n asterisk target, and a space complexity of O, target, where n is the length of nums and target is total_sum/2. By leveraging dynamic programming, the code avoids the exponential complexity of a brute force approach, making it suitable for larger input sizes. Here, we start by importing the necessary utilities and defining our solution class with the method canPartition. The first step is to calculate the total sum of the elements in the input array nums. We do this using a simple loop that iterates through each number and adds it to the total sum. Next, we check if the total sum is odd. If it is, we know it's impossible to divide the array into two subsets with equal sums, so we immediately return false. Now, if the total sum is even, we define the target sum for one subset, which is simply half of the total sum. This target will help us determine if we can construct a subset with this specific sum. To solve the problem, we use a dynamic programming approach. We initialize a Boolean array dp that tracks which subset sums are achievable. The array is size target plus 1, with dp, 0, set to true because a sum of 0 can always be achieved by taking no elements. Finally, we iterate through each number in the input array. For each number, we update the dp array starting from the back to ensure we don't overwrite values from the current iteration prematurely. For each number in the array, we iterate backwards from the target sum down to the value of number. This ensures that we are only updating subset sums that include the current number. The key operation is setting dp, t, to true if the subset sum t can be achieved either by the previous state of dp, t, or by adding the current number to a previously achievable subset sum t number. Once we finish processing all numbers, we move to the final step, checking if the target sum is achievable. This is simply determined by the value of dp, target. If it's true, it means we can form a subset with the target sum, and therefore, the array can be partitioned into two equal subsets. If it's false, such a partition is not possible. The method then returns the result of dp, target. To solve the problem, we start by calculating the total sum of the input array. For the example, 1, 5, 11, 5, the total sum is 22. Since this sum is even, it's possible to partition the array into two equal subsets. Our target for one subset becomes half of the total sum, which is 11. Next, we initialize a dynamic programming array, or dp array, of size 12, because the target is 11 and we need to cover all sums up to and including the target. Initially, dp, 0, is set to true, as a sum of 0 is always achievable without including any numbers. Now, we process each number in the input array and update the dp array. Starting with the first number, 1, we iterate backwards from the target, 11, down to 1. For t equals 1, dp, 1, is updated to true because dp, 1 to 1, is true. This means a subset sum of 1 is now achievable. Moving on to the next number, 5, we again iterate backwards from 11 to 5. For t equals 6, dp 6 becomes true because dp 6 to 5 is true, and similarly, dp 5 is updated to true. At this point, the dp array reflects that sums of 0, 1, 5, and 6 are achievable with the numbers we've processed so far. Now, we process the number 11. For t equals 11, dp 11 is updated to true because dp 11 to 11 is true. This indicates that a subset sum of 11 is achievable, which matches our target. At this stage, the dp array confirms that the required subset can be formed. The second occurrence of 5 doesn't change the dp array since all relevant sums for this number have already been updated. Finally, we check if dp 11 is true. Since it is, we return true, indicating that the input array can indeed be partitioned into two subsets with equal sums. For the second example, 1, 2, 3, 5, we quickly calculate the total sum as 11. Since the total sum is odd, it's impossible to create two equal subsets, so we return false immediately. Similarly, in the third example, 2, 2, 3, 3, 4, 5, the total sum is 19, which is also odd. Again, we can conclude right away that partitioning into two equal subsets is not possible, and we return false. To analyze the time complexity of this algorithm, let's break it into its components. First, we have the operation to calculate the sum of the array, sum, nums, which takes n time since it involves iterating through all the elements of nums. Next, we initialize the dynamic programming table, the dp array, which has a size of target plus 1. Here, target is equal to total underscore sum // 2. Since the sum of the array elements is proportional to n, in the worst case, the size of the dp array can be approximated as os, where s is the sum of nums divided by 2. Initializing this array therefore takes os time. Finally, we process the array elements. For each number in nums, the algorithm iterates backward through the dp array. This involves an outer loop that runs n times, once for each element in the array, and an inner loop that iterates at most os times, from target down to the current number. Together, these nested loops contribute n*s to the overall time complexity. Adding up all contributions, the total time complexity is n plus s plus n*s. However, in practice, the n*s term dominates when both n and s are large, so the effective time complexity is n*s. Now, for the space complexity, the dominant factor is also the dp array, which has a size of target plus 1. Since target is proportional to os, the space required for the dp array is os. Additionally, the algorithm uses a constant amount of extra space for variables like total underscore sum, target, and loop counters. These require O1 space. When we consider both of these factors, the total space complexity is OS, with the memory usage of the dp array being the main contributor. Looking at the best, average, and worst case scenarios, we see some interesting differences. In the best case, if the sum of the array nums is odd, the algorithm exits early after the if total underscore sum %2 equals 0 check. This requires only n time for the sum, nums, operation and O1 space for the constant variables. In the average case, where the algorithm processes the dp array for a reasonably balanced input, the time complexity is n*s, and the space complexity is os. The worst case occurs when the sum of nums is even, and the algorithm must iterate through the entire dp array for every element in nums. Here, the time complexity remains n*s, and the space complexity is os. Compared to a brute force approach, which would generate all subsets of nums and check if any subset sums to target, the dynamic programming solution is far more efficient. The brute force method has a time complexity of 2 to the power of n, since there are 2 to the power of n subsets, and a space complexity of n for the recursion stack in a recursive implementation. The dp solution avoids redundant calculations by reusing previously computed results, reducing the time complexity to n*s, and the space complexity to os by using a 1D array instead of a 2D table. If we mathematically analyze the big O complexity of the algorithm, we see that the time complexity of the inner loop is directly proportional to target, which is os. Since the outer loop iterates n times, the total time complexity becomes n*s. For space complexity, the dominant factor remains the dp array, which has a size of target plus 1, making it os. These complexities are derived directly from the structure of the algorithm, specifically the nested loops for filling the DP array and the memory allocation required for the DP table. This mathematical analysis confirms the efficiency of the dynamic programming approach for solving the partition equals subset sum problem, especially when compared to less efficient brute force methods. When working on this problem, there are several common mistakes to watch out for. First, many people jump straight into writing the subset sum logic without checking if the total sum of the array is even. This is a critical step because if the total sum is odd, it's mathematically impossible to partition the array into two subsets with equal sums. Skipping this check can waste time and lead to incorrect results. Next, there's the issue of incorrectly initializing the dynamic programming table. A common oversight is forgetting that a sum of 0 is always achievable with an empty subset, which is a key base case. Without this, the solution will fail for certain edge cases. Another mistake is misinterpreting the problem as one involving permutations, where the order of elements matters. Remember, this is a subset problem, so the order of elements is irrelevant. Inefficient recursion without memoization is another pitfall. If you repeatedly compute the same states, the solution will have exponential time complexity, often resulting in a time limit exceeded error. Lastly, overlooking edge cases like empty arrays, single-element arrays, or arrays filled with zeros can lead to incorrect behavior. Always test your solution against these scenarios to ensure robustness. Now, let's focus on some practical insights, especially useful in interviews. This problem is a variation of the classic 0/1 knapsack problem, and recognizing this pattern can help you approach the solution logically. For instance, framing the problem in terms of a dynamic programming table is a direct application of knapsack techniques. Additionally, you can optimize space usage. While the standard DP approach uses O and asterisk total underscore sum space, it's possible to bring this down to O total underscore sum by using a one-dimensional array and updating it in reverse. Clear communication is also critical. Be sure to explain why the total sum must be even before diving into the solution, as interviewers value clarity and logical reasoning. Furthermore, you should be prepared to discuss the time complexity of your approach. The standard dynamic programming solution runs in O and asterisk total underscore sum, but mentioning potential optimizations can demonstrate a deeper understanding. Finally, this problem is connected to other subset sum related problems you might encounter. For example, partition to k equals sum subsets generalizes the problem to dividing the array into k subsets, while target sum and coin change also share structural similarities. Understanding these connections can help you identify patterns and build solutions faster. There are also alternative approaches to solving this problem, each with its own trade-offs. One option is backtracking, which systematically explores all possible subsets. While easy to implement, this approach is highly inefficient for large inputs due to its exponential time complexity, making it suitable only for small input sizes. A more practical method is dynamic programming using tabulation, where you fill a DP table that tracks whether specific sums are achievable with the first I elements of the array. This approach is efficient for medium-sized inputs but consumes O and asterisk total underscore sum space. To optimize further, you can use a space-efficient version of DP. By iterating backward over a one-dimensional DP array, you can reduce the space complexity to O total underscore sum. However, implementing this requires extra caution to avoid overwriting states. Finally, there's the bit masking technique, which represents achievable sums using bit manipulation. While this method can be efficient in certain scenarios, it's less intuitive, requires a strong understanding of bitwise operations, and is harder to debug. Choosing the right approach depends on the input size, constraints, and your familiarity with each method. Great job! To summarize, we solved the partition equals subset sum problem using a dynamic programming approach, discussed its complexity, and learned valuable takeaways for tackling similar challenges. If you enjoyed this session, be sure to like, subscribe, and join us for more problem-solving tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!